Hello everyone, and welcome back to our series on algorithms. In the previous video, we discussed how divide and conquer can be used to construct optimal sorting algorithms. In this video, we will conclude our discussion on divide and conquer by demonstrating how to efficiently calculate convolution, Fourier transforms, and other mathematical operations. If you enjoy this lecture, please be sure to like, comment, and subscribe. With that, let's begin. For the entirety of the course thus far, we have worked in the word-RAM model, meaning that all basic arithmetic operations have been treated as being constant time, regardless of the sizes of the inputs. However, in practice, the number of bitwise operations required to perform each arithmetic operation does scale with the size of the input. Consider multiplication. Suppose we are given two n-bit numbers x and y. To multiply these numbers with the naive algorithm we learned for multiplication in elementary school would take O of n squared operations in the worst case, since we need to multiply each bit of x by each bit of y, resulting in n times n, or n squared, computations, after which we still need to add all the partial products. Let's see if we can do any better with divide and conquer. Splitting each binary number into n over 2 bit left and right components, we have that x equals 2 to the n over 2 xl plus xr, and y equals 2 to the n over 2 yl plus yr. Multiplying these numbers together gives us x times y equals 2 to the n xl times yl plus 2 to the n over 2 times xl times yr plus xr times yl plus xr times yr. Hence, we've split the original n-bit multiplication problem into 4 n over 2-bit problems. Furthermore, since we are working with bitwise operations, addition of two n-bit numbers takes theta of n time. Hence, the overall recurrence relation is given by t of n equals 4 times t of n over 2 plus theta of n. Since 4 times f of n over 2 is greater than or equal to c times f of n for c less than or equal to 2, as f of n is asymptotically linear, we have that this relation satisfies case 1 of the master theorem, meaning that the complexity is t of n equals theta of n to the log base 2 of 4, which is simply theta of n squared. Well, this is exactly the same complexity as the naive algorithm, so it seems like we didn't really accomplish anything. Is there any way we can improve on this result? Well, let's take a closer look at the middle term. Notice that we can rewrite the central term as xl plus yl times xr plus yr minus xl times yl minus xr times yr. Hence, by rewriting this term in this fashion, we reduce the number of recursive computations from 4 down to 3, as rather than having to compute xl times yr and xr times yl recursively, we can simply compute xl plus yl times xr plus yr instead. Since it takes theta of n time to perform addition, this extra time required to sum the components of the middle term is simply included in the theta of n time required to merge. Hence, we have that the new recurrence relation is t of n equals 3 times t of n over 2 plus theta of n. By the master theorem, the time complexity is now t of n equals theta of n to the log base 2 of 3, which is approximately theta of n to the 1.585. This particular algorithm is known as Karatsuba Multiplication, and it was the first fast multiplication algorithm ever found. Let's see if we can use this intuition to develop faster algorithms for other mathematical operations. Let's return back to the word-RAM model and take a look at convolution. Convolution is a mathematical operation which takes two arrays x and y of length n and m respectively and returns an array x star y of length n plus m plus 1 such that the element at index I is given by the sum over indices j and k such that j plus k equals I of xj times yk. Using the same process as the Karatsuba multiplication algorithm, we can similarly split x star y into 3 smaller subproblems with arrays of half the size, allowing us to achieve the same complexity of theta of n to the 1.585. This is pretty good, but as it turns out, we can do even better. To understand how, we first need to observe the relationship between vectors and polynomials. Namely, if we let Cn denote the vector space of all n-dimensional complex vectors, and Cnx denote the vector space of all polynomials of degree at most n-1, then there exists a linear isomorphism between these two spaces. Namely, if we have a vector with components a0, a1, all the way to a sub n-1, we can map this vector to a polynomial a0 plus a1x plus ... all the way to a sub n-1 times x to the n-1 power via a bijection. Furthermore, we can also recognize that convolving two arrays is the same as multiplying the equivalent polynomials. Given these two facts, how do we construct an efficient algorithm to multiply polynomials? Well, consider the following observation. If we have a set of endpoints at different function values, we can define one unique polynomial f of x in Cnx, which interpolates between all the points. To do this, we simply write a system of equations for each of the endpoints xi, yi, after which we then rewrite this as a matrix equation of the following form. If we want to find the coefficients of the polynomial, we simply need to multiply the inverse of the x-coordinate matrix by the y values. If we multiply a polynomial f of x in Cnx by a polynomial g of x in Cm of x, we will get the polynomial f of x times g of x, which is in C sub n plus m minus 1x. Hence, if we can obtain n plus m minus 1 points along f of x, g of x, we can figure out what the coefficients are by interpolating through the sample points. To obtain these xy values, we simply choose any arbitrary n plus m minus 1 x values, evaluate f of x and g of x for all n plus m minus 1 points, and multiply these values together to get f of x, g of x. To evaluate, say, f of x, we simply multiply the square matrix of powers of x by the polynomial coefficients of f of x. We repeat the same process for g of x. Once we have the values for f of x times g of x, we can then find the coefficients of the polynomial using the process described previously. This matrix of powers of x values is known as a Vandermonde matrix. While this approach is quite elegant, we seem to run into a problem here. A Vandermonde matrix used to interpolate a Cnx polynomial through n points requires n squared elements, meaning that just assembling this matrix takes O of n squared time. Furthermore, multiplying this matrix by a n by a1 column vector would also take O of n squared time, meaning that this algorithm would at best still be slower than the Karatsuba algorithm. It would seem that we are stuck here. However, there are a couple key observations that we can make here. Firstly, do we need to even construct the whole Vandermonde matrix to multiply it against a vector? And secondly, are there any special Vandermonde matrices for which matrix multiplication can be performed with less runtime? As it turns out, the answer to both of these questions is yes. If we choose x sub j to be the jth power of the primitive nth root of unity, omega equals e to the negative 2 pi I over n, we end up with a special Vandermonde matrix called the discrete Fourier transform matrix, or DFT matrix for short. The Fourier transform is a mathematical operation which transforms a time series into frequency space. I won't get into all the fascinating properties of the Fourier transform at this time, but just know that it has numerous applications in math, physics, engineering, computer science, and other fields. To calculate the discrete Fourier transform of a vector quickly, we can use the Fast Fourier Transform algorithm, or FFT for short. To understand how this algorithm works, we first recognize that we can split the Fourier transform into even and odd components. Let's start with the even columns. Using the n-periodicity of omega, we can rewrite these columns as follows. Notably, the top and bottom halves of these columns are the same. Moreover, the duplicated n over 2 by n over 2 matrix is actually the DFT matrix for n over 2 elements, meaning that we can again rewrite the even columns as shown here. For the odd columns, we can observe that, starting from I equals 0, the ith row of the odd columns is equal to omega to the I times the ith row of the even columns. Furthermore, we can factor the odd columns as follows. Now that we have showed how to factor the odd and even components of the Fourier transform, we are ready to introduce the FFT algorithm. Suppose we want to compute the DFT of a given vector. To begin, we first move all the even rows to the top of the vector and the odd rows to the bottom. We then calculate the n over 2 Fourier transforms recursively. Lastly, we move the rows back to their original locations, giving us the final answer. Representing this in terms of matrix operations, we have the following decomposition. Notably, this FFT algorithm assumes that the size of the Fourier transform is a power of 2. Hence, if we want to perform a FFT on a vector with a size that is not a power of 2, we will need to add zeros to pad the vector until the length becomes a power of 2. To analyze the complexity of this algorithm, we note that we are dividing the problem into two subproblems of size n over 2, and to multiply by the diagonal matrix is simply theta of n, meaning that the merge step has complexity theta of n. Hence, we have that the recurrence relation is given as t of n equals 2 times t of n over 2 plus theta of n. Since theta of n equals theta of n to the log base 2 of 2, which is theta of n, we apply case 2 of the master theorem. Hence, the FFT algorithm allows us to calculate the Fourier transform of a vector in theta of n log n time. Before we use this result for convolution, we must also determine how to efficiently compute the inverse FFT. To do this, we simply substitute omega for omega inverse and multiply the result by 1 over n. Using these results, we can now formulate a more efficient algorithm for convolution. First, we resize both our vectors by padding them with zeros until the length of each is equal to the lowest power of 2, which is greater than or equal to the sum of the lengths of the original vectors minus 1. This ensures that we can perform FFT on these vectors whilst also allowing enough space for the final result. Second, we perform element-wise multiplication between the vectors. Lastly, we apply an inverse FFT to this product, giving us our final result. Since the FFT computations dominate the runtime of this algorithm, we simply have that the worst-case time complexity of this convolution algorithm is theta of n log n. As practice, try using this algorithm to multiply the polynomials 1 plus x and 1 plus 2x. Feel free to just multiply the DFT matrix against the vectors directly, as running the FFT algorithm by hand can be very tedious. Here's an animation of this calculation on screen. As an aside, there's also another neat interpretation of using the discrete Fourier transform to perform convolution. When dealing with continuous functions, you might know that the Fourier transform of the convolution of two functions is simply the product of the Fourier transforms of the functions themselves. Hence, if we want to compute the convolution, we simply take the inverse Fourier transform of the product of Fourier transforms. Discretizing the Fourier transform from a continuous function to a vector gives us the algorithm that we employed here. This concludes our discussion on divide and conquer algorithms. In the next video, we will take our first look into greedy algorithms. Thank you for watching, and I'll see you next time.